Welcome back, everybody, for a new colloquium of the CMS. It's my pleasure to introduce today's speaker, Bianca Viray from University of Washington in Seattle. She got her PhD in California from Berkeley under the supervision of Pune. After this, she was a postdoc at Brown before joining University of Washington. As researcher, received several recognition, such as the NSF Career Award. She's a fellow of the American Mathematical Society and the Association for Women in Mathematics. And she recently got the AMS Joan and Joseph Bierman Fellowship. And today she's going to talk about isolated points on curves.
Thank you, Giovanni, for the very nice introduction. And thank you, everybody, for being here. So this talk was prepared in Seattle. So that's on the ancestral lands of the Coast Salish, Duwamish, Stillaguamish, and Suquamish nations. So the work I'm talking about today is joint work with, well, most of the results of mine that I will mention is joint work with Abby Bourdon, Özlem Ejder, Yuan Liu, and Francis Odumodu. And so if you notice, we have very convenient placement of vowels in our initials. It is Belov, which is apparently also a not uncommon Russian last name, but I don't mean a Russian mathematician. It's just our initials. Yeah, that's right. Okay, so before I start talking about isolated points on curves, I want to tell you what I mean as an arithmetic geometer as points on curves. And it's Friday afternoon, probably all ready to rest for the week. So we'll start with a warm-up question. And number theorists in the room are not allowed to answer any of my warm-up questions. Okay, so is there a right triangle with every side length rational? Okay, great. People are like, is this a trick question? Yes, I'm seeing lots of nods. Okay, so let's do this out. So we have our triangle with side lengths A, B, and C. We want each of those to be rational numbers, but then we know they can't be arbitrary because they form a triangle. We have this Pythagorean theorem that tells us that A squared plus B squared equals C squared. And not only is there one, but we also have infinitely many. And there's one silly way I can make infinitely many is that I can start with a triangle like this, maybe a 3, 4, 5 triangle, and then I can just take one of the corners and scale it up and pull it and scale by rational dilation factors, and that will still preserve every side length being rational. But I can also find infinitely many, not in this silly way, infinitely many that are distinct even modulo scaling. Excuse me. Okay, so let's step it up a little bit. So now I want to fix a positive integer n. And now I want to know if there's a right triangle with every side length rational and with area n. No answering. Okay, so let's go through again. So now we want the same side lengths ABC to be rational, and so they should satisfy the same equation, but now they're going to satisfy this additional equation that the product of A and B is twice this integer I started with. This is a little bit less obvious. Maybe some of you are, have this great idea in your head to make this very natural change of coordinates, and then you change it to a single equation. And you're asking now for x, y, and z also all non-zero for this to be satisfied. And this answer, well, for some n, so if I start with my 3, 4, 5 triangle, then that has an integer area 6. So certainly I know there are some where the answer is yes, but not for all of them. So it depends on n. This is called the congruent number problem. And if you want to see which n do satisfy this property, you can check out the online Encyclopedia of Integer Sequences and see the list of them. But one interesting thing that that happens in this case is that when the answer is yes, when there is some x, y, and z that satisfy this equation, there are actually infinitely many x, y, and z that satisfy this equation. Okay, so that's more than we need, but it's true that we get infinitely many. Okay, so these are examples of what I mean when I talk about curves. So these equations, they define nice algebraic curves in P2. So what I mean by that is if you graph this object over the complex numbers, you get something that's one-dimensional as a complex manifold, and it's compact, and you have no singularities. Okay, so that's what I mean by nice. But since these geometric objects, these complex manifolds, are not only given to me in terms of charts, they're given to me as these polynomial equations with rational coefficients. That means that I can also look at algebraic and arithmetic properties, and I can look at solutions to these equations over the rational numbers. And so that's what I mean by points on these curves, is solutions in rational numbers. And in both of the examples, as soon as we had one point, then we had infinitely many rational points. And so this is really nice. You can just go along and you can find lots of points. If we had more time and if you were looking at more examples, you might notice that this is actually a very unusual phenomenon, that if you write down other curves, other equations, and you start looking for rational points, you often will have a much harder time finding infinitely many solutions. And this is a theorem, a landmark theorem due to Faltings in 1983. And it tells us when you can have infinitely many points on a curve. So it says if you have this algebraic curve over Q, then having infinitely many solutions over Q, rational solutions, which is like arithmetic property, a property that you can talk about without looking at the complex numbers. Faltings tells us that this is controlled by the geometry, that to see whether or not this is possible, you look at the complex manifold structure, you lose all of the information about Q, you look at what happens there, and you look at the genus of that Riemann surface. And only if the genus is at most 1 can you hope to find infinitely many rational points. So this is a really amazing theorem, and it's one of the only theorems we have that nicely illustrates this philosophy that we think should hold much more widely in practice, is that the geometry of the object, even though you think you've lost so much of the arithmetic information, I mean, you've gone to the complex numbers, you've lost all the nice properties of the rational numbers and these finiteness properties, but still there's enough there that you can see that controls the arithmetic behavior. And not only, so here I've actually written a special case of this theorem. Not only is it true over Q, it holds more generally over any number field K. So if you look for solutions, not just in the rational numbers, but in any finite extension of Q. So say you take Q adjoin I, or Q adjoin a fifth root of unity, or Q adjoin the cube root of 2, any one of those fields, you still only have finitely many points. So this is really surprising because this is saying, okay, maybe you have an equation like x squared plus y, something positive, sum of squares equals a negative number. Okay, then we know you can't hope to find a solution over Q, but maybe by making extensions, then we can find lots of solutions. So Faltings tells you, well, if your genus is big, if it's 2 or more, yes, you can find solutions after making extensions, but only finitely many. No matter how large the degree of the extension is, if you make a finite extension, you still only obtain finitely many solutions. Okay, so in number theory, we do this a lot, that we have theorems that work over Q, and typically, well, we ask, and then typically they do hold more generally over number fields. So I mean, those are the same for me. Number fields and Q are the same. But if you're not a number theorist, it might seem that Q has a lot nicer properties. So what's one reason why you might think of them as being similar? Well, number fields, you should think of the numbers, the values that you get in number fields. Those are the numbers that you can express to arbitrary precision in a finite amount of space. Okay, so rational numbers, you just list the numerator and denominator, and then even though there will be a decimal expansion, you know it's eventually periodic, so that's not so surprising. Square root of 5 is not going to be eventually periodic, but because it satisfies this polynomial equation with rational coefficients, you can use Newton's method to find an approximation to arbitrary precision, whatever precision you want, just by remembering the polynomial it satisfies. So even in finite space, we can express it to arbitrary precision. So that is a non-number theoretic answer of why these should be considered the same. Okay, but when you look at it from that point of view, it's not only that the number fields can be expressed compactly, but also if you take infinite unions of certain number fields, they can also be expressed compactly. They will no longer be fields. That's part of the trade-off we're going to make, but they're still expressed compactly. So for instance, if I take any quadratic algebraic number, so anything that can be written as a plus b squared of c, even though the c is varying, these are infinitely many different fields, describing all of this is basically the same as keeping track of two rational numbers and an integer. So it can, so in some sense, the union of all of these quadratic number fields takes about the same amount of space as a cubic number field, in some sense. Okay. So going back to this question of when these curves have solutions over number fields, you might just want to know about the solutions over number fields because those are the solutions that you can describe precisely, that you can actually say on the nose that these are solutions to arbitrary position. So then this suggests, well, I mean, I don't necessarily care if the solutions are over q adjoint square root 5. What if I just care that they're over q adjoint square root c for any number c? I can still describe that in some finite amount of space. Let me consider those kind of solutions as well. So that takes us to the definition of a degree d point. So you should think of this is like a point defined over a degree d extension, but I'm agnostic about carrying around the extension that it lives over, just that it is some degree d extension. So informally, it's just if the coordinates of the point generate a degree d extension. So let's look at some examples. So if I take this cubic equation in P2, so this has a rational point. So if I plug in x and y are 0 and z is 1, that's a degree 1 point. I could also set x to be -2 and z to be 1. And then you see I get a quadratic equation in y. And probably that's too much to do in your head. So you just have to take my word for it that if you solve for y, you get this from the quadratic formula. So that's a degree 2 point defined over a quadratic extension. And if I instead set y and z to be rational numbers, say I set them to be 1, then I get a cubic equation in x. And in this case, x cubed minus x minus 2 is an irreducible polynomial. And so a root of that polynomial will generate a degree 3 extension. Okay, all the examples I did so far, these were cases where I set all but one of the coordinates to be a rational number and then solved for the other. So certainly that is one way to make them, but it's not the only way. But the other ones are a little bit more annoying. So if you take this polynomial and you plug in square root of 6 for x, again, probably you're going to have to take my word for it, that it works out that the right-hand side is 56 squared times 6. So again, you're taking a square root, but you're not taking a different square root. You still take just the square root of 6. It's already defined over that field. Okay, so this is degree d points. And so one of the main things I want to talk about today is this theorem of Faltings. So this is a great example of geometry controls arithmetic. And here, this was focused on the arithmetic property of having infinitely many points over a fixed finite degree extension. And so I'd like to think about what should the analog be if instead of asking for infinitely many k points, you ask for infinitely many degree d points. What condition goes there? Okay, so that's what I want to think about. And so again, these having infinitely many degree d points, this is having points over extensions of degree d, but where I allow which extension it is to vary. Okay, so this is different in flavor than what we did before. I meant to mention at the beginning, I really love questions. So if you have any questions, do not hesitate to ask them. Okay, let's go through this. And I love questions and I love examples. So we're going to go through an example. Okay, so we're going to consider double covers of P1 or double covers of the Riemann sphere. So I'm going to take this algebraic equation, which you can just also think of as the double cover of the Riemann sphere, branched over these 6 points, 0, 1, 2, 3, 4, and 5. So this is a genus 2 curve. If you were to graph it, you would get a donut with 2 holes. And so Faltings' theorem tells us that we can only have finitely many rational points, and also only finitely many points over any finite extension. But if you look at this equation, we're going to have infinitely many degree 2 points, because I can plug in anything I want for x, any of the infinitely many rational numbers that I know and love, and it's a quadratic equation to solve for y. And not only is this true for genus 2 curves, I can make donuts with many more holes by adding branch points to this double cover. And I can get a genus G curve for whatever G I want that still has this property that has infinitely many degree 2 points. So what this tells me is that the genus is not a strong enough invariant to detect this arithmetic property, that this property, arithmetic property of having infinitely many degree D points is a much more subtle property than having infinitely many points over some fixed field. And I need more knowledge of the geometry to detect what controls that. Okay, we're going to do this example again, but with pictures instead. So this is my curve. This, let me try to do it on here. So this bottom curve, this is my P1. So that's the Riemann sphere. I drew it as a line because I'm thinking about the rational points, which live inside the real points. And so the real points is the equator on the Riemann sphere. So you just get a line. And then this top, these are the real points of this curve. So this is like, so you think of this as sitting inside some XY plane somewhere else, and then we're projecting down to the x-axis, and this is giving me the y coordinates. There. Okay. So the base, that's my P1. So that's just the x coordinate. There's infinitely many rational points on there. So that's my cartoon of infinitely many, just all over the place. Okay, there's some of these rational points that are special that are branch points of this map. So above it, there's a sort of a double point, but if you think about the coordinates, you're just going to find one coordinate that satisfies it. But at all of the other non-special points, so the green slashes that aren't covered by pink dots, above those, you get 2 distinct Q-bar points or C points. And I've drawn them together like this, like with this X. I don't know, you think of like atoms glued together, an atomic bond or something, because the base point is defined over Q. And this map is defined over Q. So the Galois action, the Galois group of Q is acting on this whole picture. And since it fixes this and it fixes this map, it moves those, it fixes this pair of points. So those points can't be sent anywhere else. So that's why I think of this line is like the Galois action holding these two points together. So it can happen that you could get lucky, and like some of these points, it looks like you're solving a quadratic, you're taking a quadratic extension, but that just oh, wait, sorry. Okay, I forgot to do one more thing, which is that in between, there are also still quadratic points, but they're not on the black lines because those are defining imaginary quadratic extensions. So those are when I'm taking the square root of a negative number. They're still complex numbers, but you can't see them, so they're not on a black curve. Okay. Okay, and then with those, it can happen, so for the green ones, it can happen that those actually are a square. So like that, actually the Galois action just fixes this point individually and fixes this point individually. And that can happen a few other times. There we go, a few other times. But Faltings' theorem tells me it's only going to happen finitely many times. So for most of the rational points, most of the rational points along the base, these infinitely many rational points, the fiber will be one of these like molecules of these atoms stuck together. And so now you see, I mean, this is the geometric picture of where all these infinitely many degree 2 points coming from. They're just coming from the rational points on P1. And so like in my head, this is like a fun arithmetic geometry version of like Super Mario. And you just run along the base and collect all these stars corresponding to these quadratic points. And it's like super easy Super Mario because you just keep running and get as many stars as you want. Okay, so that's like, yes, we get them, but okay, it's this very easy way of doing it. And so what do we as mathematicians do? Like this constant moving goalpost, we're like, oh yeah, but that's not really what I meant. That's like a very easy way to get them. So I'm going to give that a name. And so then I can just move that aside and be like, now what else can happen? So this is the giving this a name part. So I'm going to call a degree D point P1 parameterized if it comes from a picture like this. So if there is a degree D map from the curve to P1, where the degree D point maps to a degree 1 point, maps to a rational point. And otherwise, it will be P1 isolated. So in this picture, the x's are P1 parameterized. And this map shows you that they're P1 parameterized. So you get that for free. And then you have to do a little bit more work, but it's not too hard because D is 2 in this case. You can show that all the circles in this picture on the curve, the circles on the curve, those are all P1 isolated points. Those are degree 1 P1 isolated points. Yeah?
I'm confused because are they all? Didn't you show us this map?
Oh yeah, but what's important in the map is that you take a degree D point and the map has degree D as well. So this is a degree 2 map. So it shows that the degree 2 points that get collapsed are parameterized. Yeah, but the degree 1 points, you have to show that there's no possible degree 1 map. Yeah.
Are there examples of E parameterized where it is an elliptic curve?
Oh, great question. Great question. Hold on to that thought. Okay. So let me, hold on to that thought. Okay, so, and one nice thing that happens when your base is P1 is we have this nice theorem essentially due to Hilbert, the Hilbert irreducibility theorem that says if you have a degree D map, then this will produce for you infinitely many degree D P1 parameterized points just by running along the base, just like we did. So even if you don't start with a point, even if you don't have those x's, if you have this map, you'll be able to find the x's. Okay, so then Carlo predicted the next question. So we could ask if maps to P1 are the only way we get infinitely many degree D points. So if you pause and like faithfully rewind your internal recording of what I said and replay it for yourself, you will realize that basically the only thing that we used was that the base curve had infinitely many rational points. And then if you rewind your internal recording even farther, all the way back to the beginning of the talk, you might remember that, wait a minute, Faltings' theorem had 2 possibilities of genera where I could have infinitely many points. I could have genus 0 or genus 1. Okay, that's great. So we could basically take this picture, and it's a cartoon anyway, and so we could just pretend this bottom line at the bottom is an elliptic curve, a genus 1 curve instead of P1, and we could run the same game. Okay, so I'm going to say that a point is AV parameterized if it comes from a picture like this, but where the bottom, you have to allow an elliptic curve, and then unfortunately, you also have to allow higher dimensional abelian varieties. So abelian variety is a higher dimensional generalization of an elliptic curve. And yeah, you need to allow them. So I'm going to flash up the precise definition of what AV parameterized means. If you have never heard these words before, just ignore it and focus on the picture, and just the bottom now can be slightly more general. But there is something more precise that can be said. Okay. So we have these 2 kinds of ways that we can parameterize degree d points. So we can move along a P1, or we can move along an abelian variety. And so the point is going to be parameterized if you're parameterized by either one of those objects. There's some way of moving you in a family, and it's going to be isolated if you're neither one of those, parameterized by neither of those objects. Okay, so this is partitioning all of the algebraic points on the curve which is of any degree. So there's infinitely many algebraic points on the curve, and it's partitioning them into these two classes, to being parameterized and being isolated. Okay, so how do we think about the differences between them? Well, we really defined what parameterized points were, and they came with this structure. And so whenever you have something, an object that is defined by some additional structure, usually you can use that additional structure to study the object even more. So these parameterized points come with these maps, they come with these objects that parameterize them, and those, I mean, the informal way I say is you can think of those things as casting shadows that can be understood using geometry, understood using geometric techniques. Yeah?
Okay, so the way you phrase the definition, for every point there was a single map. Is there any sense in which one map gets most of the points? Or is it really point by point? Because in your cartoon, there was one map that seemed to have.
That's right. That gets a lot of the points. That's a really great question. I think I'm going to say more about this towards the end, but please ask if you don't feel like I answered it, ask me at the end, because it's a thing I love to talk about. Okay. And so what about isolated points? Well, isolated points we defined as not being parameterized. And basically, anytime you have a mathematical object defined in that way, just like, okay, what does that mean? So, okay, we can actually say a few more things about what it means to be isolated points. So the first point is, I'll come back to this in a minute, is that there's only finitely many of them. And this might be very surprising because this is of all algebraic points on the curve of any degree. So there's infinitely many on any curve, and only finitely many of them are ever isolated. Yeah, this is like, what? Okay, and probably, I mean, I wouldn't call this a conjecture, but you know, if you put together all of the different philosophies and conjectures that exist in terms of rational points and degree d points, and you would probably guess that, okay, if I took like a typical curve for some sense of typical, then you expect that they don't have any isolated points. Okay. The first one is a theorem. The guess is a guess. The first one is a theorem. Yeah?
Is the first one your theorem, or is it?
I'm going to come to that on the next slide. So then I will clarify. Yeah. Yeah. So, okay. So you have these isolated points. Yes, we don't have structure to understand them, but the things that we can say about them, I don't know, they seem even weirder. Like I have this finite set out of these infinitely many algebraic points. So I stand by my what base, I still stand by it. Okay, but this division, this is what we get at. This division, the reason why we have to consider higher dimensional abelian varieties, and this definition that I told you to ignore because I didn't want to get into the details, it's sort of forced on us because this having parameterized points is exactly the thing that tells us when you have infinitely many degree d points or not. Okay, and so this is basically a corollary of a stronger theorem of Faltings that generalized the earlier theorem that I mentioned. You have to apply it sort of over and over and over again. So it takes some work. That's why I put plus epsilon in our paper. Yeah.
That sense that for given C there are finitely many A, you consider?
For the AV?
Yeah.
Yes, sort of. So from this theorem, then how you get that there's only finitely many isolated points is when the degree is large enough, by Riemann-Roch, you know that every degree d point is parameterized. Okay, that doesn't mean anything to you, that's fine. By some standard argument, which is a very commonly used theorem, if the degree is large enough, then everything is P1 parameterized. So you only have to look in finitely many degrees. And this tells you in those finitely many degrees, you only, well, okay, I guess as stated, it doesn't, but the argument will tell you that there's only finitely many isolated points in each degree. Turning the crank on Faltings theorem over and over again gets you that. So Jake, the answer to your question is it's mostly Faltings theorem, but you have to apply it over and over again. And so that's what we do.
Like, do you know, because I was going to make this the scope of tonality of curves, like the P1 part of the definition.
Yes,
Are there examples where it's really like coming from the AV part?
it's like all of you saw my slides and it's just like, are like, wait, but what about this question? Okay, so my claim is that this is the analog of the Faltings 83 theorem, what I said that we wanted to prove. And you might say, well, this looks like two things involving arithmetic, because P1 parameterized and AB parameterized both use arithmetic, but you can turn this into a geometry controls arithmetic statement using these geometric shadows that I talked about. And yes, the geometric shadow word is gonality. So having an AV parameterized point bounds the gonality. And P1 parameterized point also bounds the gonality. So having these are giving you a condition on the gonality. And Carlo, your question was about the abelian varieties that you have to consider. So yes, there are only finitely many. Basically, what you do is you take the Ueno locus of the image of sim D inside of pic D for all of those D. And since the Ueno locus is Zariski closed, that has finitely many components. And you look at each one of those components and the finitely many D. And that's not something I expect to make sense to everybody in the room, but it's not necessary to go on as well. Okay, great. I love all these questions. Any other questions? Yeah.
Yeah, so if you construct
Uh-huh.
any technique to transform the where the degree is less than the modality.
Yes. Yeah, that's right. So well, I think, I mean, okay, I guess I don't know how to I think I could construct a curve that contains some number of isolated points. Oh, actually, this is also the next thing. So I think this is probably the best you can say without any assumptions on the curve, because definitely if you have higher genus, all the rational points are isolated. So just like I can polynomially interpolate a curve of high degree through as many points as I want, you should be able to interpolate a high degree curve through as many low degree points as you want. And that would give you isolated points. Yeah, I think I don't know. I mean, I guess you have to construct the curve that contains the points. I don't think you can, I mean, once you have the curve, the points are either isolated or parameterized, so you don't get to finagle them. I don't know if that completely answered your question. Yeah?
Is there an upper bound on the number of isolated points in terms of the geometry of the curve?
That is also a great question. So I think, so there's like one further division of isolated points that I'm not going to quite get into in this talk, but they're called Ueno isolated points and non-Ueno isolated points. And so there's recent results of Gao, Ge, and Kuna, building on work of Dimitrov, Gao, and Habegger, that bounds the number of non-Ueno isolated points in terms of the rank of the Jacobian, the genus of the curve, and the rank of the Jacobian and the genus of the curve. So in that sense, it's bounded. If you like put together all the conjectures, people probably also think that the number of Ueno isolated points is uniformly bounded depending on the rank and the genus, but that is much harder. And then think all of those things you can also get bounds on in terms of like different heights of the abelian varieties, and maybe you could hope for better bounds, but I don't know those bounds off the top of my head. So these definitions, these definitions of parameterized and isolated points are in, I mean, there's similar to things that appeared, but this exact phrasing of them and the way that we tease them out is in our paper. So there are a lot of prior work that I think will give you consequences for isolated points, but it hasn't completely systematically been gone through because previously it was looked at just for like degree D points or for fixed degree or rational points. Yeah, so I think there are bounds, but they're not all written down. Okay, so I'm slightly 2/3 way through my talk, and we built up the question I asked at the beginning, we answered, and I said this is the strongest statement that we can do without assumptions on a curve. So like, where are we going to go from here? So to answer that, I want to like do a brief philosophical detour and first think about, well, how is it that we study curves? So if you're a grad student, or when I was a grad student, and if you decide that you want to study the arithmetic of curves, you go to your advisor, you're like, oh my God, this is so cool. I really want to study the arithmetic of curves. Like, how do you get started? Does your advisor like hand you a stack of curves and be like, okay, here you go, get to work. Just you pull one out and start working on it. And then when you're done the next day, when you go through the stack, maybe that's your thesis. So as I think, judging by the face of many of you in the audience, you're guessing that that's not the case. The way that we study curves is we study them with the viewpoint of modern algebra. We study curves in their category. So we don't study them as standalone objects in a stack that are unrelated to everything else. We study them keeping track of their morphisms to other curves and thinking how they relate to other curves. So we should not only want to know how isolated and parameterized points behave on a single curve, we should want to know how they map along things. So we want to know how they study, how they, okay. I think there's like some delay in when I'm pressing. Okay. I'm worried that at some point it's going to like do 10 transitions at a time. Okay, well, we'll just deal with that if that happens. Okay, so let's take a morphism of curves. So what we prove is that if you have a point on your source curve and it satisfies this condition, which you should think of is its degree is as large as it possibly can be, given the degree of the image and the degree of the map. And so if you have that property, this point, then the property of being isolated is preserved by this morphism. So if you started with an isolated point, it pushes down. Okay, so if we look at this organizing with the tower, what it suggests is when you have some curves, as long as this degree condition is satisfied, and so that's why this is a lemma and not a theorem, but as long as the degree condition is satisfied, you could think of the isolated points as trying to like percolate down these maps. Okay, and sometimes in talks I am tempted to call this a theorem and sometimes have, because even though the statement follows rather straightforwardly from the definitions, I feel like the philosophy that it says is very powerful. And so we'll come to this. Okay, so now we have these curves and we're keeping track of their maps to each other, and we know the isolated points move down, but like, where do we start? Do we have like one curve that rules everything? Well, we don't quite have that, but we do have some curves to rule those all. And those also go by the name of moduli spaces. Okay, so moduli spaces are these really amazing geometric objects that parameterize other geometric objects. And so when you understand the arithmetic and the geometry of the moduli space, if you understand it well enough, you basically understand the arithmetic and the geometry of like everything else. So yes, really does rule them all. Okay, and often moduli spaces are organized by different discrete invariants. and they arise in towers. Okay, so there's this particular one, x1 of n, which we'll talk about, and it comes in a tower that's infinitely tall and infinitely wide. It's organized by positive integers by divisibility. Okay, and so it's infinitely tall and infinitely wide, but our lemma tells us that we should think of these isolated points as wanting to, like, I don't know, like a pinball machine wanting to come down this tower and percolate down. Okay, so just to repeat this, I'm really going to drive this home. So we don't know for sure because we have this condition on the points, but assuming this condition on the points, the presence of the isolated points should likely be detected low in the tower. So when we started working on this project, we'll see in a minute when you think about it in terms of modular curves. Well, okay, so these modular curves, they tell us about the arithmetic of elliptic curves. So elliptic curves are genus 1 curves with a fixed choice of a point. And if you don't know, this is a really good number theory test. If you ask somebody what an elliptic curve is, if they just say genus 1 curve, they're not a number theorist. If they say genus 1 curve with a point, then they're a number theorist. Okay, but it's really important. I'm a number theorist and I'm speaking, so I can have my chance for propaganda. Why? Because when you fix a point, it tells you where to take like a basis for your fundamental group. We get to cut open our torus and unwind it, and now embed it in the complex plane. And we can put our point at the origin, and that gives us a group structure. But we needed our point. Okay, so the moduli space, or the modular curve x1 of n, the geometric objects that it parameterizes are elliptic curves together with a point of order n. Okay, so when we started this project, we were talking about studying the rational points on modular curves, and a very well-meaning and kind remark that we often got is like, well, don't we know everything about torsion on elliptic curves? Which is very reasonable remark because we have this amazing theorem about torsion on elliptic curves. This is one of my favorite theorems. It's a theorem of Morel. And it tells us that if you fix a positive integer g, then for all number fields of degree at most d, and all elliptic curves defined over those number fields, the torsion is on that elliptic curve is bounded by a constant that depends only on the degree. This is just like totally and completely mind-blowing. I can't believe that this is true. It's so amazing. This is the best theorem. Okay. So let's see what this very amazing theorem tells us about isolated points. So because it tells us about isolated points on modular curves. And we should expect it to tell us something because this tells us about torsion on modular curves, torsion on elliptic curves, and the modular curves parameterize torsion on elliptic curves. So by this some curves to rule them all, you know, it's supposed to say something. And so what it says is if you fix a positive integer g, there is a constant so that if you take n bigger than this constant, so high enough up in the tower or farther to the right in the tower, if you have an isolated point, its degree is really big. So what that tells you is that as you go high up or to the right in the tower, the isolated points get harder and harder to detect because their degrees are really, really big. So they're defined over number fields of really, really high degree. We can't do anything for those cases. But what does our lemma say? Our lemma says, don't look high up in the tower. Why are you looking high in the tower? It's hard to find things high in the tower. You should look low down in the tower because you will see shadows of those isolated points low in the tower. Okay. So I just want to be very clear. I'm not disparaging Morel's theorem. I love Morel's theorem. It's amazing. I think this just shows you how little we know about isolated points because the theorem that's so amazing that tells us so much tells us so little about isolated points. Okay, so let's look at this lemma applied to modular curves, and now we're really going to have to deal with this hypothesis. So what we are able to show is that if you take this tower that's infinitely tall and infinitely wide, so the wide part is kind of annoying. So we just have to chop that off. So we're just going to look at this tower, finite width tower. And then what we can show is that if you look at the non-CM isolated points high up in the tower that correspond to elliptic curves defined over the rational numbers, that you can detect them below some bounded line. And we give explicit formulas for what these bounds are. It's like a lot of divisibility conditions on the 18 on the ends. So yeah, so this likely thing does actually turn out to be true in practice. And this, I mean, it's not so great that we had to chop it off. So conjecturally, if you assume this folklore conjecture, which is a generalization of a conjecture of Serre, then you can remove this chopping off. But if you want an unconditional statement, you have to chop it off to finite width. Any questions?
Your muse, man. Or it's.
I don't think we use Morel. No. We're studying, I mean, we are using a lot of things about Galois representations to get, but we're mostly just we're using mainly Serre's open Ibn theorem. And so before Morel proved his theorem, I think it was Manin proved a theorem that was only in the tower of modular curves that were prime power level for a fixed prime. And the arguments that we're using are the same type of arguments that go into Manin, but not that go into Morel. Okay, I haven't thought about this enough. My guess is that maybe that's also partly like if we could leverage what Morel does more, then perhaps there would be another way to remove this cutting off. But yeah, I would say that that's more of the difference.
Just to make sure, so can be detected below means that if I have an isolated point above this.
Yeah, it means that if you find all the isolated points below this line, then every isolated point above it, that's a non-CM one corresponding to elliptic curve over Q, maps to one of those.
But we understand also that like
when you can lift it, we don't understand. I would have guessed that for non-CM isolated points, they can only be lifted to isolated points to like some finite number of lifts. For CM isolated points, you can lift them infinitely high up.
but otherwise it's fine.
Well, that's what I would have guessed, but it's we can't prove it. And I don't know if it's just that it's a very difficult statement to prove or that maybe there is some way to lift it. I think sometimes the intuition on isolated, because their degree is allowed to grow big, sometimes my intuition messes with me because I'm used to think like.
An isolated point, it's not just knowing that the Galois isn't the singularity, the Ejder Galois representation is finite index or something. It's not enough to say.
I don't think it's enough. You have to know, because the thing is that you don't have enough control on how the gonality grows relative to how the level grows. I think if we had better control on the gonality, then it would be enough. Yeah.
Can I ask sort of a naive question about your lemma, about the lemma about descending things that was debating looking low in this tower? What I didn't understand, so if you have your map from a curve C to D, C only has finitely many isolated points. So like, what is it the case that given this map, most of the points satisfy that degree condition that you wrote down? Because what if just those finitely many ones are exceptions, then they wouldn't necessarily pass down.
Yeah, that's right. They might not pass down. And anytime you map to a P1, they won't pass down because P1 doesn't have any isolated points. So you can have that happen. But as you go higher up in a tower, So that's why you want to apply this to towers, because if you go higher up in a tower, the genus is large, so that you think, yeah, so there is this tension that you are articulating, which is that we do expect most points to satisfy this degree bound. Because if you don't have a reason for the point to factor, like for the degree to shrink, it should be as large as, that's the typical behavior. But it's also true the isolated points are already not typical. So like maybe just, so I guess the hope is, especially when you look at a tower, it's like that shouldn't be able to happen all over the tower. So maybe it happens a few times, but it shouldn't be able to happen all the way. And so that's what we prove here, that if you're above, basically that's what we're proving. If you're above this line, then the isolated points do satisfy this degree condition, and so they will get pushed down. Did I answer your question? Okay.
So just one.
Yeah.
So if I understand what you said, then you are also expecting the non-CM points are finite in that now. Because then you can detect them from below, and each of them you said there are finitely many steps.
Yeah, the non-CM isolated points. Well, okay, so I mean, I will say I initially thought that we would be able to show that there's only finitely many lists. And now I don't know. Yeah, I don't know. It might, I mean, if you like really made me guess, like put a gun to my head and made me guess, I would probably still guess that there's only finitely many lists, but I just have yeah, it's really just a guess, and it doesn't seem easy to prove. Okay, so in my last few minutes, I just want to talk about a few things that we can go from here. So the theorem that I just presented, together with this folklore conjecture that I said allows you to remove that line, chopping it to finite width, it tells you that isolated points on this tower corresponding to non-CM elliptic curves over Q lie over finitely many J invariants. So there's finitely many elliptic curves, non-CM elliptic curves over Q that correspond to these isolated points. And so like, very natural question is, what are those J invariants? So two of my collaborators have followed up on this. So Ejder has some theoretical results in this direction, particularly for isolated points on prime power level curves. And then Bourdon led a collaboration to try to search from all of the elliptic curves in LMFDB, whether they give rise to isolated points in the tower. And so these are the only 4 from the LMFDB that give rise to isolated points in the tower. Why those 4? I don't know. We don't know yet. But yeah, so that's one question. Okay, so this was about isolated points. So let me go back. So second direction, follow up where you could go is going back to parameterized versus isolated. I told you this nice story about parameterized points being better understood because they come with this structure. Really, if you dig into it, really what is better understood is how they arise, like where these families come from and what contributes to them. But if you asked me like, okay, is there a point over a degree 5 extension where the prime 7 has this splitting type or this ramification, or like any other number theoretic questions that we ask about the number field, we don't know. So, and this question about isolated points, that there's only finitely many of them, like, yes, that just like, I'm like, oh my God, these points are so mysterious, I want to study them. But also it's like sort of a red herring, because it's those isolated points, they're only telling you, because there's only finitely many of them, they're only telling you a very small bit of the arithmetic of the curve. The arithmetic of the curve is mostly contained all in the parameterized points. So we should like use this structure we have to better understand those points, which will give us a better understanding of the arithmetic. So this is going in the wrong order. So I'm actually trying to understand these points. I'm working on that right now with Irma Balçik, Stephanie Chan, and Yuan Liu. And Yuan, I think, just spoke here a couple of weeks ago. Okay, and then the third direction, which like is very tantalizing, but I think still just interesting questions right now, is that you would want to know like, hey, is there some modular explanation for these weird points on a modular tower? So the weird points on an arbitrary curve, you can't really hope for an explanation because like we talked about before, you can rig a curve through many isolated points and like you just rigged them to be there. There was no deeper reason for their existence. But on the modular tower, maybe there's a reason. Maybe there's a reason for these isolated points. And CM points and cusps are often isolated. There's a reason for those. So what about the non-CM and non-cuspidal points? I think this is very tantalizing. I think it's very difficult. And I also think it's possible that the answer might be unsatisfying. Like, I think there might be a modular explanation, but like almost tautological modular explanation. But yeah, I think it would be really interesting if there was an explanation that was not as tautological. And I think I'll end here. Thank you.
Thank you very much for the beautiful talk and more questions from the audience.
So I guess that if you have a curve of hydrogenous, all the Weierstrass points and all those things, they're not isolated. All the kind of special points on the curve that emerge from the film.
I would have to think, I don't think they're necessarily isolated. So like on a hyperelliptic curve, if the Weierstrass point, so say you have a genus 2 curve and the Weierstrass points are, it's a single Galois orbit, then their degree will be 6. And so then they'll be parametrized by Riemann-Roch. So they maybe have a chance of being isolated, but they're not necessarily going to be isolated.
I would put that they were not.
Not isolated or not parametrized? Oh, yeah. Yeah, I think it depends on the Galois orbit on them, because if they're all rational, then they will be isolated. But if they're stuck together, then their degree will be bigger than the genus, and then they'll be parametrized.
It's really an error.
Yeah, that's right. Right. Yeah, you could think about, and I have wondered whether we should do this. You could think about whether a divisor is isolated or parametrized, an effective divisor. And so then the Weierstrass points, so say for a hyperelliptic curve, if you don't take the point itself, but you take twice the point, then it will always be parametrized, basically by virtue of it sitting in this hyperelliptic family. So that might be more of the reason that Weierstrass points don't really come naturally as points. They come as points with ramification, and that multiple is what helps you see the behavior.
If you call it P1 parameterized, is it known whether the small is the where you get infinitely many and the gonad is the one side?
Yeah, so the degrees of the P1 parameterized points is exactly the degrees of the maps to P1. So the smallest one is the gonality.
No, the smallest degree where you get infinitely.
Oh, where you get infinitely many points. Yeah, so this is, so Isabelle Vogt has looked at this a lot. So she looked at this first in a paper with Jeff Smith, and now more recently in a paper with Boris Kadetz. So we've renamed this the minimum density degree is the smallest degree for curves where you get infinitely many degree d points. And it's between, I have to get the bounds right. It's always between at most the gonality and at least the gonality over 2. And Smith and Vogt show that for every gonality and every number in that range, there is a curve that realizes that gonality and that minimal degree.
This is sort of the minimal degree such that the curve has infinitely many points of that degree.
That's right. Yeah. Yeah. So you can think the minimal degree where the degree d points are Zariski dense on the curve. That's why we call it the minimal density degree. Yeah. For small d.
Yeah.
No. Well, so I mean, there is a curve that realize where it is the gonality, but it doesn't have to be. So for instance, like you could have a non-hyperelliptic curve that's a double cover of an elliptic curve with positive rank. And then it will have infinitely many, it will have density, minimum density degree 2, but not ganality 2. But there is, maybe what you're thinking of is there are results of Harris-Silverman and then Abramovich-Harris that show that if it's, you have minimum density degree 2, well, okay. What they show is that if you have minimum density degree 2, then geometrically you're a double cover of P1 or an elliptic curve, but it might not, you might not happen over the ground field. So you might be having infinitely many degree 2 points not arising from a cover. Wait, hang on. Yeah, I think that's right. That's right. Yeah, and then Harris and Silverman showed this, no, sorry, Abramovich-Harris showed the same thing for degree 3 and for degree 4, as long as it's not a genus 7 curve. And then there's a counterexample in degree 4 and genus 7.
About CM curves, is it completely understood there or?
Which ones are isolated?
Yeah.
I think it's pretty completely understood. So there's, in our paper, there's a section that shows like when you can lift them and like which prime levels the points will give you isolated points. And then I think in follow-up work with Abby Bourdon and maybe Lori Watson and some other people, I think we completely know for CM.
If there are no more questions, let's thank the speaker again.